Welcome everyone back to the point distribution webinar. Thanks for joining us today. Today we have with us speaking Jonathan Passant, who will be talking about configurations and Erdős style distance problems. As always, after the talk, there will be time for questions. Then after that, there's time. We'll have a tea time if anybody wants to stay around and chat for a bit. Jonathan.
Thank you very much, and thank you for the organizers for inviting me to speak. Okay, so today I'm kind of, oh, that's not going as, oh, there we go. Okay, so today I'm kind of going to be talking about two papers. They're both kind of on the same theme, discuss kind of different aspects of one problem. And so the first was published jointly with my PhD advisor, Alex Josevich, and it's about rigid graph distances. And the second one is about Hamiltonian graph distance. So we'll get into both of these kind of results as we go through. Okay, and so I want to start extremely simple. So I apologize to people that might know these kind of things before. But so for kind of the majority of this talk, we'll be thinking about discrete points in the plane, so in 2 dimensions. And when we say a distance, we're just talking about the regular Euclidean distance between 2 points. And so this is, and then I'll denote them using this notation. And so kind of one of the central objects of study in kind of discrete geometry for a long time has been distance sets. And for me, this will be taking some finite distance set P and taking all pairwise distances from it. And the reason this has kind of been very useful to, well, so what we mean here is kind of distinct distances. And so on the left-hand side in this kind of square lattice, all the red distances would be counted as one distinct distance. And the group blue ones also one. And so, whereas if you have some kind of random set, you're going to kind of get P squared distances. So in some sense, you can look at configurations where you're trying to minimize distances. And the worst possible example is some kind of random set. Okay. And so you have this kind of very trivial bound coming from pairs. And so Erdős in the 1940s kind of started this by defining this function, which asks across all possible point sets of a certain size, what's the smallest view on this? And so the idea is that we'll kind of examine the asymptotic behavior of this function in terms of n. So as your point sets grow, what does the smallest number of distances a set look like? And in this original paper, you can count the kind of root n by root n lattice, and this requires a bit of number theory. There's a theorem of Landau and Brajaneman that kind of says that the number of solutions to the quadratic form you get out is going to be roughly n over square root log n. And so when you see kind of epsilons popping up in the remainder of the talk, this is kind of normally in 2 dimensions, this is due to kind of number theoretic considerations that generally will kind of brush under the rug. Yes, and so this shows that, you know, we always have this root n by root n lattice asymptotically, and that we can kind of bound it up to constants by n over root n. And so if you see these squiggles, it means I'm hiding some kind of constants when I talk about these. And so there are various questions that can be asked. Kind of the most famous is the Erdős distinct distance problem, which asks for the asymptotic behavior of this. And Erdős said that it should be both bounded above and bounded from below by n over square root. And he also asked a bunch of other questions, kind of like, if you are in this optimal scheme, are you a lattice necessarily? And no one really knows how to answer this question. This is extremely open. But there has been significant progress on. So there was originally Erdős's result in 1946, where he proved the law of n to the half. And this is a very simple argument. And this was expanded over the years. Subsequently, you know, there's an n to the 2/3 argument, there's an n to the 4/5 argument, just kind of incremental work. And this is kind of nicely summarized for those who are interested in a book of Garibaldi and Josevich and Sanger. They kind of talk about most of these, but they don't talk about the resolution because it was published just before. And this is the theorem of Ghostcast in 2010. and they prove the lower bound of n over 1. And so this is kind of believed to be kind of essentially closing the problem, because getting any closer to this would be kind of a much more number theoretic result than most of the attempts thus far. Okay, and so our closely related conjecture, which will come up a bunch today because it's related to the problem in configurations, is the pinned distance conjecture. And this is, so again, we've got this kind of definition, but the idea here is we take a point set and you say there must be, instead of these distances occurring throughout it, there must be kind of one individual point from which almost all of these, which a positive proportion of these distances occur. And so what we do is we take this buoy point here and we measure all the distances out from it. And we call this buoy point the pin. And we say, well, how big do we expect if you have n points in your set, what's the richest pin? And so the conjecture is the same as with the distance conjecture. So we expect n over square root log n distances to occur from one point. And this is very easy to see with the grid, because if you take the point in the lower left, any distance can be translated down there, and so you will get this. But it's not necessarily obvious that this should be true over all point sets. But that's the conjecture. And again, Edish's original proof for the distance conjecture also kind of gives a result for this one. And the best known, certainly that I know of, is the result of Katz and Tardish in 2004. And one of the main kind of advancements that allowed the proof of Gus and Katz was kind of a decoupling of the distance conjecture itself from this harder pinned version. So this is still open. And in fact, almost any question you can ask about this is still open. Okay, so Park asked a variant of this, which is if you take n points, how many distinct classes of similar triangles do you get, where the vertices of these triangles must be points in your set? And so you can kind of look at a random set, and if you think about this again, you'll expect about p to the 3. Whereas if you look on a line, I think you get, what is it? Yeah, p squared. So they prove this result with the lower bound n squared over log n, and they do this by looking at an instance problem in the complex numbers. So this is a theme that will come up a lot today, is you have this problem about points and you translate it into incidence problems, and then you come up with a good instance bound, and this provides you a good lower bound. Okay, and so one can, the question was originally asked about similar triangles, but one can ask it about congruent triangles. And so we're stopping this kind of scaling that can happen. And you would expect maybe the result to be significantly better when you start to, because you're getting many more kind of objects. And so there's a theorem of Rudnev that says you can remove this log from it. And so scaling really only costs you a logarithm in the bound. Okay. And so what I really want to talk about today is larger configurations. So you can think of the distance problem as being a 2-point configuration where you're talking about the distance in between. Triangle problem is a 3-point configuration, but how do you look at large configurations? You've got 4 points or 6 points or some kind of small number of points relative to your asymptotic set. And so when you talk about larger sets, you suddenly have these two different notions of what it means to be congruent. There is kind of the first notion, which says, well, I'll consider two kind of, in this case, 4-point sets congruent if there is a unique rigid motion that takes one on top of the other. So here we can just see that this is a rotation. And then there's the second notion of congruence that says, well, I don't want to necessarily specify a uniform motion. I just want to talk about the distances. So I specify some number of distances internally, and so they're congruent if these certain specified distances are the same. Okay, and so these are going to coincide for triangles, but they don't coincide for larger circles. Okay, and so we set up a very similar scheme for this. so it turns out the rotational congruence version of this is going to be very easy. And this is because this uses essentially the technology that Gus and Katz developed. And so we set up a similar kind of notion, the number of congruence classes of these, so you have to rule out singular versions of these that you don't necessarily want. And you can then set up a very similar notion. So this is just asking of all point sets of a certain size, what's the minimum number of realizations we expect? And you can quickly prove that this is bounded by the n to the number of vertices you have minus 1. So this is where this n to the k minus 1 comes from. Okay. And so we're going to just quickly go through the proof of this because this is a very simple proof that kind of illustrates the kind of basic setup for all the proofs that I'll be talking about today. And so the idea is just kind of a simple Cauchy-Schwarz energy situation. So you take this V of t, which measures all of the possible things that lie in one congruence class, and you apply Cauchy-Schwarz. And then you see that you get, this p to the 2k as a lower bound times the number of such distinct ones, and then the second term you get is an energy term. So this measures all tuples of, well, all pairs of k tuples where they're in the same congruence class. So for those of you familiar with additive energy or multiplicative energy, this is a very similar concept. And now we use kind of the idea or the definition in this case that if they exist in the same congruence class, then there must be some unique rigid motion that takes one to the other. And we can see that any rigid motion that must take one of these k tuples to a different k tuple must be at least k rich. And so then you do the counting kind of backwards, and you say that, well, suppose it's R rich, then there must be these R to the k such pairs of k tuples. And so you rearrange your sum and you get something like this. And so the key idea that we're going to then use are these Ghostcast lines that come from this. And so there are two types of rigid motion. The first is a translation, and these turn out not to be too important because we're in 2 dimensions, and so the translations are just 2-dimensional. Whereas the rotations are 3-dimensional and are much more of an issue. And so the Ghostcast lines, you can kind of, if you want to get into the group theory of this, this is, kind of a, you can take the group of rigid motions, you select one of the kinetic components, and you, because you have a finite number of points, you can kind of project this into 3 dimensions in a nice way, in a way that you don't end up with any overlaps or anything. But you can kind of very naively think of it as if you've got a rigid motion that takes p to p, rotation, sorry, that takes p to p prime, it must exist on the perpendicular bisector, and then you lift it into 3-dimensional space depending on the angle. So here the z coordinate tells you the angle, and the xy coordinate tells you the center of rotation. And so what happens when you have an incidence of 2 of these lines in 3-dimensional space, the projection of that down into the xy plane will tell you the center of your rotation. And because they've got the same z coordinate, it's the same angle of rotation. And so an incidence between the line LP and P prime and LQQ prime means that you take P Q, the line PQ, to the line P prime Q prime. And so this is taking a distance, a pair of distances, and translating that pair of distances to now an incidence of 2 lines in 2 dimensions. So this was kind of the key observation of, well, first of Ellerkish, and then it was simplified by Katz to allow it to be lines. And this kind of gives the main breakthrough, well, one of the 2 main breakthroughs to the Ghostcast proof. Okay, and so we should think of intersections now as meaning distances being the same. So this will come up later when we talk about this distance complex. Okay, and so the second main breakthrough of Gus and Katz in the 2010 paper was they then proved a very impressive incidence bound as well. And so the main things that you should think about when you look at this is, firstly, to make it truly 3-dimensional, you have to restrict the number of lines that lie in a plane. And the second one is that you have to restrict the number of lines that can lie in a regulus. you can think of this as a degree 2 kind of variety, if you wish. And if you do this, then there can't be too many intersections. And so they proved that it can't be more than the number of lines to the power of 3 over 2 over r squared. And this is enough to get the bound that they proved. And so this is good because we already have this bound, and it doesn't, our points that we are concerned about are just k-rich to be at the minimum. And so we can use this, right? This corresponds to all richnesses. And so we plug this into what we did before. You use telescoping, which means that your sum will be efficient, and then you plug this in and you get the sharp result. And so just to summarize this, you kind of start off with the Cauchy-Schwarz energy bound. You take your energy and you convert it to rigid motions. And you use rigid motions to convert to incidences, and then you prove an incidence bound. So it will generally go some kind of trivial energy bound to begin with, some kind of translation into incidences, and then some kind of incidence bound. Generally in 3 dimensions, and because we're in 3 dimensions, we'll need these kind of 2 conditions about planes and about regular. Okay, so that was the first one, and it turns out to be very easy because it's essentially already the Ghostcast proof. The second one requires more work because it's not a uniform motion. So Ghostcast is very good at dealing with uniform motions, it's not very good at distinct ones. Okay, and so how we're going to set this up is we define a graph to tell us which edges we care about in terms of this congruences. So if I have my graph as kind of the 4 cycle, then I care about fewer edges. But if I say that it's the complete graph on 4 vertices, then I care about all possible edges. And you can see in the second case, you're already going to have restricted yourself to, if you have all those distances defined, there's going to be a uniform motion to take one to the other, right? You've kind of over-specified it in a sense. Whereas in the C4 case, you're going to have some wiggle room. So there's a possibility that you have 2 that have the same distances, but you've somehow pulled and squished it a bit and no longer have a uniform motion. And so in some sense, rigidity is going to help us. And this was kind of the second result of the first paper. So before we get to this, we will say that we expect this just to be dependent on the number of vertices in your graph. And so for a connected graph, we expect kind of the lower bound to be number of vertices -1, and we have this epsilon loss that covers things, as we'll talk about later, like chains. And so there, the number theoretic considerations will come into effect, and you have to be a bit careful. Okay. Cool. And so, as I said before, this is very simple when it's a rigid graph, and so you have to be slightly technical on what you mean by rigid. And so we technically mean minimally, infinitesimally rigid. And once you have this, then this kind of comes almost automatically. You end up with this log term, which I don't think should really be there, but I'm not able to remove it. Somehow loops within graphs mean that you should have fewer log terms. And if it's rigid, then you should have enough loops to get rid of them all. But we weren't quite able to. Okay, so this kind of relies on a theorem of Chapman-Santony, Yurcevich, Spatarian, and Pakianathan. And this essentially says if your thing is minimally infinitesimally rigid, then you will get a positive proportion of your pairs in your energy, such that you have exactly what you want. So if all the edges are green, then we do have this rigid motion. And then the proof follows kind of exactly as before. And I should note at this stage that really the only reason why this doesn't work in higher dimensions is because we've not solved this kind of distance problem in higher dimensions. So both of these cases kind of reduce to the kind of count of rigid motions. Okay. And so we just start talking about now non-rigid graphs. Now this is the case where we generally have, non-unique motions. And so the easiest of these is what I'm calling the 2 chain. So I'll call chains the number of distances because they're kind of more what I care about than the vertices. And so this is the two chain, and you can see you have so much flexibility with where the second one goes while still maintaining the distance that you're never going to get average motion. Okay. And so the first kind of progress on non-rigid graphs was made by Misha Rudnev in 2019, and he proved a sharp up to logarithms bound for the two chain. And once you've got it for the two chain, in the triangle, you've got it for all graphs on 3 vertices. Okay. And so the new results that I want to talk about today are expanding this to kind of any connected graph with a Hamiltonian path. So if you take any graph with a Hamiltonian path, you now have up to these log factors, which you expect to be there for, as you see in the second result, you have a sharp bound. So here, the logarithm term is not efficient. It could theoretically be improved, but the exponent in n is good. So we're up to an epsilon factor of n sharp here. And so this is derived from the result on K-chains, which is the same thing as the lower bound, but you can see from the upper bound that you do get what these log terms cropping up. So to kind of get rid of them for some graphs, you would have to you'd come up with a different kind of idea. Okay. Very good. And so I just want to point out that both these results are valid because it's very easy to construct a rigid graph without a Hamiltonian path, something like this. The triangles are going to make it rigid, but there's no way you can visit all of these vertices because you have to visit the internal ones too often. And so, yeah, so this is going to resolve this graphical air disk conjecture, kind of a large class of graphs. And the only thing that we have left in terms of this conjecture that we can't really do are star graphs. So these are where you have one central point and a lot of spots coming off from it. And this is where I've related back to this kind of harder problem that we don't know how to solve of the pinned air disk problem. You kind of already see that coming up with this central point and many things coming off it. Okay, so yeah, so the barrier is the following. So it suffices to prove for spanning trees, mainly because it's only dependent on vertices. So once you have the spanning tree, it's got the same number of vertices and we're done. And there is no bound for K stars bigger than the two hinge right now, of the two chain, I have to say. And so estimates on these stars would give pinned edge bounds. And so you can show that if you have a bound on an efficient bound on the K star, then you get quite an efficient bound on the pinned edge conjecture. So something on the 8 star or above would be the best known result and beat Captain Tardish's 2004 result. So these stars are of interest to me. If anyone figures out a good way to make progress there, I'd be very interested. Okay, so stars are kind of the enemy, but we're not going to talk about stars because I don't have to do them. So going back to Rudnev's proof, because my work relies quite a lot on kind of some of the ideas he introduced. The idea is very much similar to the proof we talked about before. So you start off with the energy step, and this means you need to count these pairs. So you have these two pairs of hinges or two chains, and you see you want to convert these into an instance vector. And so the way you do this is looking at these two ones. You have one rigid motion that takes the first distance to the first one, and this leads to an intersection between the red line, which is the one that moves all the rigid motions that move the first red dot to the second, and a blue line that moves the first blue dot to the second. And then the second blue line comes from moving the second blue dot to the second. And so you end up with this kind of structure in 3 dimensions that you now want to count. There is one central line and these two spoke lines coming off it. And so you have to count these kind of things and come up with some kind of instance bound here. Okay, so how Misha figured out how to do this is some kind of double partitioning argument. And so you take your lines and you partition them first by the number of points of essentially richness kappa, and then you say, well, I want approximately t points of richness kappa on these. And then once you do this, you can use if you have a low weight, which is, you make sure that the points are not too, when you sum across all these intersections, you don't have too much going on. You can use a line result of Frank Pursuit. And if you have a high weight, then you have to be more clever and you put them in a polynomial surface, and then you have to use an incidence result of Scherer and so on to kind of get this result. But it's still kind of fundamentally the idea of this energy step is the first one, then you prove some kind of. Okay. And so the incidence bound of Rudnev, firstly, you need, again, this insistence that you don't have too many points in a plane or a regulus. And if you do this, you get this very nice result. And this is kind of, to me, the first kind of weighted version of a Ghostcast type result. And so you can also think of this as giving an L2 bound across all lines. So if you sum across all lines, number of lines that intersect it, this is exactly what Ghostcast proved a sharp bound on, and this gives you a sharp bound on the number of pairs of intersections of lines that go across this. So it gives you an L2 bound. And the reason the K star is so difficult is it's an LK bound on such words. So we have an L1 bound and an L2 bound, but getting an LK bound seems tricky. And in fact, we have an example for stars that means that the energy step, kind of the first step in this, the energy step won't work. So there's something that gives you too high an energy for that to be a valid approach. Okay. And so the proof of this result is going to be this similar outline. You use a Cauchy-Schwarz kind of energy bound to begin. Once you have the instance set up, you can make a nice observation that means you don't need to count odd and even change. You can just do it for one of them, which saves you, half the work. And then you have to iterate. So as we'll see later, you end up with a central point that you kind of span out from. And as you get longer and longer chains, you get more and more spanning out from the central point. And so you end up with this horrible iterative line set. And then you basically have to keep the hardest part of the proof is keeping everything accounted for. Okay. And then you want to generalize this earlier theorem of Rudnev that I put up to allow one. You don't really want to deal with these iterative line sets because they're dealing with how their structure progresses as you iterate on them is the best. So you end up using the global structure of the original line set. And to do that, you need to generalize the result of Rudnev. Okay. And this gives you this iterative instance. Right. And so, as has come up a couple of times already, if you have, when you start up with the energy step, you want to count pairs. And so if you take pairs of 3 chains, this is the incident structure you get on the bottom. You end up with, 4 lines coming from each kind of pair of points. And then the incidences mean that the distances are the same. So this first incidence between L P1 P1 prime and L P2 P2 prime comes from the distance between P1 and P2 being the same between P1 and P2 prime. And this is the same all the way along. And so you think of the central point, and we're going to think of things coming out from the center. Okay. And so now we have to kind of partition points. We partition our points so they have roughly T1 lines coming through them that have roughly T2 lines coming through them. So now instead of just taking your one line and partitioning it, you're looking at points that have this nice structure coming out from it. And then using this partitioning, you can kind of prove the following kind of energy bound. And so you need now an instance bound on these kind of points. And with 5 chains, you get even longer things happening upstairs, right? And you can see now that we're stepping out from the central point once on each side as we move our chain up by a length of 2. And so a 7 chain would have even 2 more lines coming off this, etc., etc. And so this is how the iteration is going to work. And so, yeah, so you end up with, if you've got a K chain, you end up with K plus 1 over 2 variables. Then you need to prove some kind of iterative instance bound to get to kind of wrangle all of these together. Okay. And so the good news is you don't need to come up with some separate scheme to do this for even chains. So even chains, instead of having a central point, have a central line. But you can kind of split this up. So you take one point that's on the central line, and then you split it up as this slightly longer chain, which turns out to be, so here we have a 4-chain. The red part corresponds to half of what we get in the 5-chain case, and the blue part is half of what we get in the 3-chain case. And so by solving the 5 and the 3 and using Cauchy-Schwarz, we solve the 4. And so this turns out just to lighten out a little bit. It's quite nice because there's already a lot of counting to do. Okay. And so we want to estimate the setup here, which is points that have roughly T1 lines through them that have this iterative structure. So they have this line has roughly T2 of the first intersection, that has roughly T3 of the second intersection ad nauseum. And so the way we do this is we use this generalized theorem of Guth and Katz. And again, now there is this parameter that kind of talks about the structure. So S is our structure parameter, and it talks about the number of kind of lines that can line up in. And so in our case, we noticed that all of these iterative lines within our original line set, and our original line set already has a structure that we know is good, because we know at most L to the half of them can within any point. And so this is where you see this L to the 1/2 coming up in the middle term, is using the global structure of the lines that we started with to deal with these iterative sets all the way along. And so this is the key idea that we'll be using kind of as we go into all this iteration. Yeah, and so we need it because otherwise we can't use efficient theorems. And as I've said before, this is an absolute nightmare to try and track the structure. And so given that each time we do this kind of iteration, they still line the big set, we use the global structure. And this turns out to be enough, which is fortunate. So we're always, whenever we see an S, we're going to think of plugging in the global kind of L to the 1/2. And this is kind of what we're going to use for any of these sets in any point or rectangles. Okay. And so with this in mind, one can prove the following set kind of theorem, which you take any line set whatsoever, and you make sure that it has a certain type of structure, then you can again count this kind of iterative set. And so the first term is kind of exactly what you would see coming from this Rudnev result. If you replaced S with L to the 1/2, you get the L squared that originally cropped up. And this second term here is unfortunate, but it's what happens because we no longer have such good control over planar segments. And so, yeah, we have much worse control in linear components of things. And so the proof is essentially the same as Rudnev's, but with a lot more bookkeeping. And over linear components, you have to use point-point duality in R3 to make sure that there are not too many. There cannot be too many of these lines in a point because there can't be too many for a point. And once we sum over kind of all possible things, we end up with the following kind of rich line theorem, which is the one that we're going to use. And this is where a bunch of those log terms that are quite inefficient get introduced at this stage, along with the partitioning stage where another bunch of log terms get introduced. And so we then have to, basically, as we go along this iteration, we see which bucket each T falls into. Either the T is going to be small, in which case we can kind of put it into the first bin, or it's not going to be, it's going to be quite large, in which case it goes into the second bin. And so we just keep track of all of these, and we end up with the following absolutely horrendous theorem. But it turns out to be exactly what we need. You end up with this. And then the way that this resolves is you have this on the one side, and then you notice that your point set that you iterated is just can just be thought of as the original Ghostcast point set. And so you can apply their bound. And so then you have these two bounds and you play them off against each other. And then once you've done all the kind of bookkeeping, you get the bounds necessary to kind of bound all these energies. Okay. So yeah, so it works with kind of what you would expect. You have this Cauchy-Schwarz energy argument, which you count pairs of chains. You end up with this incidence problem, and we count from the central point, and the even chains follow from the odd ones, and this incidence result turns out to be quite messy, but it's not too difficult. You kind of iterate the line partitioning and be very careful on them. Use the global structure to allow you to use the more efficient results in R3, and you kind of generalize this theorem of Rudnev, and this allows you to kind of pass on, and at each stage you're not doing anything too bad. And then you weigh your careful accounting up against this chance. Okay. So just to summarize where we are with this graphical conjecture, we have it for kind of Hamiltonian paths and rigid graphs, but it's unresolved for step graphs. And the second kind of very subtle point that I also don't know how to improve, but you can kind of see working, is that when loops are present in these graphs, the log terms can be minimized. I don't think there is a nice way to, well, I don't know of a nice way to kind of put this into any proofs and get any nice results out of, but it's a thing that can be done. Well, I believe it can be done. Okay. I think that's all I had to say. I didn't want to go into too much detail because as you can see, it's already very technical. So I think that's all I had to say. If anyone wants to ask me about any of it, please do.
Thank you very much for a nice talk. Let us thank the speaker. Please, some questions or comments? Okay, maybe I'll start. Do you have some suggestions about your conjectures, which are correct bounds for the estimate, like at the beginning and the later as well?
Sorry, what was that at the end? I missed it over the internet.
I just want, do you have suggestions? What are the correct lower or upper bounds for your estimates? You have a lot of estimates, for example, at the beginning, yeah, sure, and later. Do you have what are your suggestions? What is correct results?
Oh, so the annoying thing is that the result changes depending on the number of loops. So for chains, if I can find where I put that result, I believe that like k/2 is the correct number of logarithms. Where so this upper bound here, I have no reason to believe is not the correct one. The issue comes, so this is for chains, and if chains don't have any loops, but if you have, for example, a chain of triangles, you should be able to cut off a logarithm for every one of these triangles. And you can just see this because the kind of freedom you have to act once you've chosen, two of your distances in the triangle, the last one is kind of determined in kind of a very strong way. And so this extra logarithm term shouldn't be there. And this is kind of backed up by that earlier result of Misha Rudnev on the congruent triangles. Like you can see him getting rid of logarithms, and this same thing happened in that first kind of rigidity, right, where you have this uniform motion. We had no logarithms there. So the exponent of the n, with the n to the k-1 is certainly sharp. The logarithms, I think k-1/2 is kind of the worst case scenario, but it would, yeah, you should expect better when you have loops, but I've not thought of a clever way to write this down, I suppose.
You think that the upper estimate is close to the right estimate, right?
For chains, certainly. I would be very surprised. I mean, the problem with this is like all distinct distances, you look at a grid and go, this is the correct answer for the grid, and I don't see any reason why this shouldn't be true. But there is no necessarily evidence other than, no one has found a smarter thing to say about it.
And also, like usually, like to find the correct low estimate is more difficult than to find upper estimate also.
Yeah. No, it's a kind of a nightmare for upper estimates. You can, so if you look at other lattices, you get similar estimates. I've not done this with chains necessarily, I didn't double check it. But for just the original distance problem, there are kind of three types. Well, triangular lattices, square lattices give you the same thing, and you construct a third type of lattice that has also n over root log n distances. And Erdős conjectured the lattice that, originally conjectured that only square and triangular lattices could do this. And then someone, Adam Scheffer and Ben Wood found a third type, and then they conjectured that those three were the only type. So it's this kind of thing where no one really has, it's kind of folklore more than it is supreme confidence, I suppose. So that's the correct upper bound.
Yeah, I understand. Thank you for your answer. Please, some other questions, comments? Okay, maybe people.
I have a quick. Okay, I'll ask after we turn.
Please.
Yeah, I'll ask when we turn off the recording.
Oh,
okay.
Actually, I think Ryan should stop recording, but.
Ryan stopped recording already. Oh, okay.
No, he should stop it, but
Ryan,
he probably something with connection.
Oh, he's not here even.
He was, but then he just disappeared.
Okay. Anyways, yeah. So I guess I can be on record. That's fine. My question is, it's sort of very vague. Are there continuous analogs of all these things? Like for the Erdős distance problem, right? There is a continuous analog, which is the Feltner conjecture.
Yes, absolutely.
Okay.
So my advisor, Alex Josevich, which I'm sure some are familiar with, and Crystal Taylor.
I know Alex very well.
Yeah. I think him and Crystal have a paper together that did this for trees, which for me, trees is the entire game, right? If I can get a tree, then I'm done. This was prior to the decoupling era, so I don't think the bounds on that are necessarily as good as they could be these days. But yeah, I think they ended up managing to peel things back to a tree, and then once you got the tree, you proved the result for this, and so it turned out to be quite nice. Yeah, so I looked into that a little bit, and then I can't remember. Alex was telling me they had issues with. There's certainly issues there. They haven't quite managed to resolve it for all graphs, I think. But we kind of have opposite issues, right? He has the ability to do it for trees and not for more complicated things. And I have the ability to do it for chains, but not quite trees yet. So where there are analogs, but they kind of diverge in what's difficult, which is frustrating.
Okay, thanks.
Please, some other questions or comments? Okay, it's not the case. Let's speaker once again. Thank you, very nice talk. And we could have now some coffee time, but actually Ryan should stop.
I'll stop sharing my screen.
Yeah.
Sorry for being a bit short. I'm generally extremely quick.
It's okay.
But there's only so much you can. I could have spent another 10 minutes talking about that, but I don't think anyone is necessarily profoundly interested in me going into all the accounting of that. I didn't like
No,
doing it myself. that much.
I think it was just the right amount of details. Yeah, I think it was,
Yeah.
yeah,
That
Yeah,
was
so
when I talked.
it's weird. It's weird. Ryan disappeared, right? So we're still being recorded. So yeah, and
Oh,
don't
yeah.
say anything you don't want on record. You just
Oh
leave.
no, I think anybody that reads that paper will see that there is too much accounting.
Yeah, no, yeah.
But
I think
just
I think
joking,
only Ryan have permission to stop recording because
I see.
yeah.
Okay.
Oh, 1 second.